So, and these two guys cancel and give us 1, right? So we end up with a 1 on the top and 1 plus 0, or 1 on the bottom. And as long as this is a finite number, then the theorem here tells us that since L is finite, then we have same series, either both of them converge, which is the case, or both of them diverge. So looks like they both converge, again, because of geometric series on the bottom. So doing the problem 2 times, I'm trying to convince you that there is no single solution for these exercises. In fact, we're going to enter in the next section now, and you will see another test that will be presented. But again, all of these tests are actually giving you the same results, either convergent or divergence for the series. And if you utilize that limit comparison test, or if you utilized the test that is called term comparison or series comparison, the one that we just had above, the result is always the same. And that's a nice part in mathematics. Then no matter how you do the problem, your result is the same. The answer is the same. And that's, I guess, the nice part of it. And you will see more tests in the following sections of this chapter to test series and their conversions. And you can utilize those tests, or you could utilize the test that we already learned before. Well, it turns out we'll learn some very, very useful tests that are much nicer than these. So you'll definitely be excited. But the point is, they're not always possible to perform, and that's the reason why we start in this way. So I guess we're gonna move on to the next section. I think it's enough if we do a few problems on this page, because then it's just repeating the stories again and again. And there are actually interesting exercises, as you can see, like maybe problem number 45 or something from this group of exercises. Because if you try to see what's going on here, it may not be that obvious, but if you notice that all of these could be factored with 1 over 200 out, then I'm going to have 1 plus 1/2, right? Then next will be 1/3, 1/4, and etc. So you basically have harmonic series hidden here, right? So you can say it's the same as 1 over 200 multiplied by series from 1 to infinity of 1 over n. And remember that this series is going to be a divergent. So point is, if you do more problems, you will keep doing the same thing, basically. So you find that it's 1 over n. So you're not going to get anything really much different with what we already saw before. And that's why I'm saying it's important that you just concentrate on what we do in class, because yes, you can spend hours and days doing every single little exercise in these sections, but you're not going to utilize any new ideas. It's already been stated. And that's why I highly recommend you over weekend to try to redo the problems that were done in class, because that should be plenty for you to learn. So now the next section is talking about series that called sign alternating. Notice if you add and then you subtract, and then add again and then subtract again, it looks like this series will converge easier than if you just keep adding more and more and more. So if you subtract it, you're kind of making it smaller, even though you added something, but then you're making it smaller. So there is more chance intuitively, right, that series is going to converge. And they call sign alternating series. And sometimes we can write it with a first term being negative, and sometimes with first term being positive. So for example, here we have a series that actually starts at 0. And I think you can also have this series start at 1 and go to infinity, because one can say why 0 is here. Well, you can start at 1, but then you're going to have the powers of -1/2 raised to the power of n minus 1. So if you start with 1, then it'd be n minus 1, and you can double check for n equal to 1, the power will be 0, and that's exactly how we get first term of it. So it turns out it doesn't really matter. If you start with a 0, your series, or you started with index 1, of course it does make a little bit of a difference, but the difference is in adding one term. And that one term does not make any difference for conversions or divergence, because it's just one number. So if your sum of series is infinite, if you have extra number in or out, that's not changing anything at all, right? So that's the point of story, that we don't really need to worry much about the first index, whether it's 0 or 1. Sometimes formally we, for example, when you end up with some like ln, then you don't want to have a ln of 0 because it's undefined. And so that's why people try to start with 1 when you're dealing with natural logarithm in your series. So just to make sure that it is all in so-called domain. But these sign alternating series have indeed one positive, one negative, and so forth and so forth. And it turns out that for sign alternating series, it's so much nicer in terms of convergence, because all you have to do is have nth term going to 0. So let me find, where's that statement? I think I skipped it. So it's much nicer to work with this series, because all they want is to have, remember, the statement used to be if series convergent, then nth term has to go to 0. And we actually never could utilize this to prove things, but what we could utilize is so-called contrapositive. So we were saying, if not that, remember how we produce contrapositive argument. If A, then B. But the contrapositive, which is equivalent to this statement, negates both of them in reverses direction. So it says not B, then not A. So the contrapositive here will look like if
recording in progress,
your nth term does not, see, we have to negate, go into 0, then the series is not convergent. Not convergence means divergent. And that's what we heavily utilized, right? If you look at the nth term, so if it goes to 0, then we have, if it doesn't go to 0, then we have divergent series, right? The way we used it. Because again, there is no way to utilize this, because they say if series convergent, then the nth term goes to 0, but we need to find that series is convergent, because nth term going to 0, like here, for example, does not tell us that series is conversion. Right? So it's possible that nth term approaching to zero, but series is not convergent. And that's why when your statement goes only in one direction, it's not strong enough. But turns out for the sign alternating series, so to show the sign is alternating, I can put like -1 to the power of n times an. Only for those, then we can say if series convergent, then nth term, of course, approaching to zero, but with extra statement backwards. So it's enough to just check the nth term, and if it goes to zero, that's it. Sign alternating series conversion. Not every series, like Connor example is here. Nth term going to zero, but this is harmonic series, which is divergent, right? We already saw this before. If you forgot, a section before previous is where we heavily utilize it, and we checked it, taking the integral of 1 over n, that was ln, and when it's infinity, ln infinity is infinity, so diversion. But for only sign alternating series, it's also sufficient for series to be conversion. And where is the test? So looks like theorem 914. Where's the theorem 914? I'm looking at it. Oh, here it is. So it says that limit is 0, then series is going to be conversion. Well, usually second condition we don't check because it's automatically present. It's, I think, very difficult to find a series that's going to have the terms spreading and still approaching to zero. I'm not sure even if they have such an example in this textbook. Anything is possible, but it's kind of formality. The point of story is that nth term needs to approach to zero, and that's good enough. So it relaxes us a little bit when we do the exercises. So let me take a look at some problems and enjoy them. So let me clear all the mess that I produced. I know the fast way, so I'm going to just stop share and then share this once again. So this way it's all going to be cleaned. So let me take a look at the exercises with a sign alternating series. So where they actually want us to check it. Looks like first page has use of graphing utility. I guess I'm not going to worry about it. So the actual exercises start here with problem number 11. So let me do it. Section 9.5. So all you care about is to take a look at the nth term. For exercise number 11, it's going to be 1 over n plus 1. When I say, Alex, what about the -1 to the power of n plus 1? We don't really care for this because it just tells us that the sign 1 will be positive when power is even, and 1 will be negative, and then again positive and then negative. So it's sign alternating series. So the nth term that we really care about is 1 over n plus 1, which approaching to 0, and therefore we have a convergence according to the theorem that says -1 to the power of n plus 1 multiplied by this nth term, which is 1 over n plus 1 from 1 to infinity, is going to be convergent. I say, Alex, but you just told us that this series analogous to 1 over n, and this is divergent. And I totally agree. But we're not talking right now about this series, which is divergent indeed. We're talking about series that has alternation in sign. You see the difference? The one below has all positive terms, but the one above has alternation in signs. So for that type of series, we have convergence. But if sign is not alternating, the series is divergent because that's analog to harmonic, right? Because we're so this harmonic 1 over n, and it's divergent also. So we see that's equivalent 1 over n, that plus 1 makes no difference. So that's interesting thing about this section, as well as there is another observation that is giving us a little extra here. It's talking about absolute or conditional convergence. And turns out this one converges conditionally. Conditionally, because without the minus sign, it's divergent. See, if it would converge without minus sign, then it's convergent absolutely. So it doesn't really care for these minuses because they just help you to converge. But otherwise, if you throw away minus signs, so if you just consider only positive portion, then if it's divergent, then series converges only conditionally. Conditional conversion. So it looks like we should pay a little attention to this when we find that series is convergent or not. So let me try exercise number 19. I think it's interesting to consider because this exercise number 19 has divergent series. Why is that? Well, look at the nth term. It's n squared over n squared plus 5. Notice the limit of this will be 1, wouldn't it? You can do the L'Hopital's rule twice, and you get 2n over 2n, and then again, it'll be 2 over 2, so the limit is 1. So it is divergent series. By all means, it's divergent. So again, even though it's sign alternating series in exercise number 19, I still don't really care about the sign. I care about the nth term. But having this sign that alternates is helpful. What about cosine with n pi, which is going to be the same as sine with n pi? Notice that if you multiply your letter pi by n, the series is going to look like, remember graph of function cosine? Like that, right? From 0 to 2 pi. So here's point pi, and is bounded by plus and minus 1. So I want you to notice that this is not really something tricky. It only has values either plus 1 or minus 1, y coordinates. So when we have this series in exercise 27, where is it? Starting at 1, then cosine of n times pi will be cosine of pi. So we're actually starting with minus 1. And then next will be 2 pi, which is plus 1. And then again, minus 1 and then plus 1. And then minus 1 and then plus 1. The limit of nth term is not equal to 0. We say, well, wait a second, Alex, but this is 0, this is 0, this is 0. Isn't the sum equal to 0? And the answer is no. You can regroup this, and notice if you group this, then this will be 0 and so forth, another 0. But what to do with -1? So is that going to be -1 then? But they're not equal to 0. So when you have infinitely many numbers to add, you cannot really use the arguments that we have for finite numbers, because infinity is just too big, turns out. We never get even close to it. If you're looking at the numbers that we know and zoom them out, so the numbers that we're actually working with, billion, trillion, what's that deficit, quadrillion or whatever, and from perspective of infinity, we're all here by 0. So the huge number, one is a Google is big number, like 1 was what, 100, 0. It's still here because infinity is much bigger. So we can't really, well, that's I guess not from mathematics. We can't really get even closer to infinity, like halfway or something, turns out. That actually makes mathematicians that trying to work with those infinities don't feel good, because they don't go under the logic that we used to have. And that's why things are not that good. So someone, a Cantor, believes they ended up at the mental institution with this infinities, because he said that he got close to it, but well, it didn't work. So psychologically. So anyways, just trying to say that these examples, if you be interested, there's a class called set theory that actually tries to put hands on the something infinite, but still they don't get close to. So that's why we just say, if limit of nth term is not 0, then series is divergent, period. We don't get into trying to get intuition. That's my point. And we just use the test. So nth term must approach to 0. Is not 0, that's it. Divergent series, period. Has a sum, does not have a sum. That's why we are not really getting to it, because looks like there are 2 possibilities already, either -1 or 0, and there'll be more if you start to study it a little more, if you start to group in it a little bit differently, and there could be some other possibilities. It's actually an interesting thing to do over weekend if you be into it. But anyways, my goal today is just to introduce you with this nth term test, and I guess it's pretty much all I could say about it. Just maybe do another couple of exercises, because it's really, I think, nice topic and pretty intuitive. So let me try another problem here. Let me try something that doesn't look that nicely. So how about if I try problem number 23? Notice there is ln here, so let us see what's going on with 23. And again, all I care about is the nth term. So without all of this mess, -1 to some powers, I just take the nth term. The nth term will look like n plus 1 divided by ln of n plus 1. So it looks like numerator and denominator will approach to infinity. So when I take a limit of this nth term, I'm going to need to maybe use a L'Hopital's rule, take a derivative, because we have infinity over infinity type of undeterminate form. And definitely numerator will become 1 and make us feel much better. And what's going to happen with our denominator? Okay. squeeze the limit here first. Well, looks like denominator's derivative will be 1 over n, right? 1 over n plus 1 here. And now you see that this is actually infinity, right? Because limit of this nth term is going to be the same as n plus 1 if you're going to reciprocate that denominator fraction, right? And when n approaches to infinity, it is infinity. And that's why series is divergent. The nth term must always go to 0. That's the point of story. So another divergent series, which is interesting. And let me try one more, and then maybe you can try one more, right? Let me try what? So if it's series divergent, there is nothing you can do at all. Let me try something that looks a little bit worse. Look at this 34 exercise. Let's try that. Of course, I'm not going to ask you for something of that type. I will ask you to do number 12. I think number 12 will be a good problem in the spirit of the exercise that I just done. But let me do number 34 for you, because that definitely looks different. So in exercise 34, again, I need to see what happens with the nth term, and if this nth term is approaching to 0 or not, right? So I take a limit of, looks like on the top we have odd numbers 1, 3, 5, ... all the way to 2n minus 1. And on the bottom, we have numbers 1, 4, 7, and so forth. So it looks like on the top, I keep adding number 2 to produce the next terms. And here on the bottom, I keep adding number 3. So does this series approach to 0? This limit. So we have 3n minus 2. That's an interesting question, right? And you can see that looks like every term gets indeed smaller, right? And smaller and smaller. So it looks like this is equal to 0 intuitively. Just look at first terms. So first it will be 1, and then here's 3, here's 4, so just 3/4. The next term will be taking this 3/4 basically and multiplying it by 5/7. So we actually have this term decreased because we took 5/7 portion of it, right? And etc. So you just keep on multiplying this by numbers smaller. So then you take this term and multiplying it again by what? 7/10. So the previous term times 7/10, and so forth and so forth. So can you somehow produce not intuition, but some algebraic description of this? Well, it looks like first number was 3/4, right? So if I just put them in the calculator, so it'll be easier to see what we're actually multiplying by. Get a scientific calculator. So I just want to list first few numbers, not in terms of fractions, but in terms of decimals, so maybe we can better see it. So for the next one, I have that 3/4, and then multiplied it by 5/7, right? So notice it's already 0.5. So what happens next? Well, then I take 3 times 5 and then times 7, that's my numerator, and then divide this product by 4 times 7, right? And then times 10. You see the terms start to get definitely close to 0, but again, how can I describe this relationship to 0? Well, I can notice that if I would multiply this not by 3/4, but by 5/7, then it's got smaller. So maybe if I just look at, keep on multiplying by 3/4, that series will dominate the one that I have. So if that's my AN, I don't want to write it again, it's taking time. So that will be dominating it, and that's convergent. So actually, this is exercise for that test I told you that is not pleasant because you need to estimate all these terms. Converge because it's geometric, right? Geometric because it's ratio 3/4, less than 1. And the one that I have here is actually smaller, looks like, right? And this way, I will get conversions of smaller series because dominating is also conversion. See, this term comparison test is not that obvious, and that's why it is worth to get a piece of paper and to actually write those terms one after another, and this way you will be able to better see all of that. So, as promised, I'll give you problem number 12 to enjoy. So if you're not sure how to do it, 11, I did something similar already. Let me give you a hint. I did 22, for example. That was similar. So for a quiz for today, please try exercise number 11. So this way you can get the answer. Is it convergent or divergent? Again, all you have to do is just say convergent or divergent. That's the answer. And after that, you can log out and have a good weekend, right? Because again, it's Thursday, so I'm gonna enjoy weekend after.